So, hello everyone, and welcome to the second day of VINCI 21. I'm happy to announce our next keynote speaker, Tamara Munzner. She holds a PhD from Stanford and currently is a professor at the computer science at the University of British Columbia. Her expertise comprises development, evaluation, and characterization of visualization systems and techniques from both user-driven and technique-driven perspective. During the last 3 decades, she authored the book on visualization analysis and design, published numerous high-ranking papers, not only in the domain of visualization, but also in graphics and HCI. And in 2015, she received the IEEE VGTC Technical Achievement Award, and this year, actually, the Achievement Award of the Canadian HCI Society. So without further ado, Tamara, the stage is yours.
All right, thank you so much for the kind introduction. Good morning to you in Europe. It's evening here for me in Vancouver. And I would like to spend the next little while talking to you about problem-driven visualization through design studies. So I'm going to frame my thoughts about visualization through a paper I wrote a while back called The Nested Model. And I find it a useful way to think about visualization, where we have 4 levels of what I'll call concerns. And so at the top level, the domain situation, we can ask, well, who are the target users? What kinds of problems are they trying to solve? But we can't stop there. We have to go from the specific vocabulary of a particular domain to some kind of abstraction, because it could be that users that are in, say, physics and finance might use very different words for fundamentally the same idea, but likewise 2 biologists might be doing something that seems to be similar at first glance, but that structurally is actually quite different. So we always want to go from domain-specific language to some sort of abstract vocabulary, what I'll call the vocabulary of visualization. Now, at the abstraction level, we're typically interested in 2 things. What is being shown? I'll call that the data abstraction. And what's interesting and tricky, as we'll talk about quite a bit in this talk, is that you don't necessarily get to just take the data set you're given and draw that. You often have to do some sort of transformation into a new form, and that's one of the really tricky things about this abstraction level of design. And then also we're interested in why is the user looking at it, and I'll call that the task abstraction. So we care about data and task, and we want to think about those in a way that transcends particular domains because we've mapped to this abstract vocabulary. And then we can address what I'll call the idiom level, which is, well, how is it being shown? How are we actually visualizing this data? And we'll think both about the visual encoding idiom, how to draw something, and then the interaction idiom, how to manipulate that drawing. And sometimes we have idioms that really do comprise both interaction and encoding, but sometimes it's more obvious where we just have one or the other. And then finally, we want to think about the algorithm level, where we've got efficient computation. And the reason I like splitting things up into these 4 different levels is it helps us make decisions about validation. Because validation of visualization is a really hard problem. How do you know if you got it right? And the answer is there's a lot of different ways to get it wrong, and they fundamentally differ at each of these levels. So what could we do wrong? At the domain level, we might simply misunderstand the needs of the user. Maybe we didn't talk to them. Maybe we just believed what they said and didn't spend time observing them. At the abstraction level, well, we might get that data abstraction wrong. We might actually be showing them the wrong thing, and then the most perfect visual encoding in the world can't save us. At the idiom level, maybe the way you're trying to show it simply doesn't work given the constraints of human perception, which are often inconvenient and sometimes surprising. And then finally, at the algorithm level, well, we might have something that simply doesn't scale. Maybe your code is too slow. These are really different families of problems. And so we typically need to steal methods from a whole lot of different fields at each level. Visualization is a really intrinsically interdisciplinary approach. So computer science usually does a great job of validation at the algorithm level. At the systems level, measuring computational benchmarks that give us system time and memory, that's something that's well taught in most computer science departments, or on the more theoretical side, maybe analyzing the computational complexity. But we can't stop there. Um, this kind of technique-driven work, it's interesting and it's very common, but it's by no means the only thing we do in visualization. So what else could we do? Well, in order to try to figure out the idiom level, sometimes we use techniques out of the design community to think about justifying and ideation, where we consider multiple alternatives very explicitly. And then in order to actually try to see if we got it right after implementing something, we could analyze the results qualitatively, or we could actually run user studies where we've got these human-in-the-loop experiments in some sort of controlled laboratory settings where now we've got a stopwatch and we're actually trying to measure human time and error rather than computational time and memory usage. And then we can't stop there either because we're not done. We have to grab methods out of the social sciences as opposed to things like cognitive psychology and HCI. The social sciences like anthropology and ethnography are really what we need to mine in order to understand, did we get the abstractions right? So we typically do need to watch people and talk to people. And then it's usually much more reasonable to try to validate with a field study. Where we actually try to see if we give real users these new tools, does it actually change how they work? And so what's tricky about these situations is we often want to have problem-driven work where we start with a domain problem, go through these levels with abstractions and idioms, design algorithms, instantiate that, and then try to understand, have we done this right? And so with this kind of problem-driven work, we typically want to go all the way through this nested model. We may or may not actually innovate. We might not design entirely new visual encoding techniques, but we want to check whether the ones that we have designed are appropriate. So this idea that there's technique-driven work and problem-driven work, there's a lot of both of these in visualization. And what we want to do is we want to try to avoid mismatches between these levels in the validation. One way a lot of people go wrong is by having a mismatch where they're presenting work and they try to convince me that, say, their idiom is correct by measuring how long a computational benchmark takes, which is an algorithm level validation technique. That doesn't tell me whether or not the people understood it. Or they try to validate something where they have an abstraction, but if you try to validate an abstraction with a lab study, you're usually telling the people what to do in the lab. It's usually more appropriate to validate abstractions with field studies where you actually deploy it and look at real-world usage, where the people themselves choose how and when to use it rather than doing what they're told in a lab. So getting these alignments right is one interesting thing that the nested model can help you think about. And so now what I'm going to do is talk a bit about using this kind of approach to do this idea of problem-driven work, where we really do start with a domain situation. I'm also personally interested in technique-driven work, and I do a fair amount of that. And then, of course, as I mentioned, this idea of how do you validate any of these are things I'm interested in as well. And then I like taking all three of these and trying to figure out, what have we learned? How can we now use this new knowledge to come up with new guidelines and theoretical foundations? But in this talk in particular, I'm really going to focus on the problem-driven work aspects and tie in a bit more of these theoretical foundations as well. We already talked a bit about the nested model. And I'll talk about one more methodological issue as well. So in the visualization community, we often call this kind of problem-driven work design studies. My still current favorite definition of that is that a design study is a project in which visualization researchers analyze a specific real-world problem faced by domain experts, design a visualization system that supports solving this problem, validate the design, as we just talked about, and then reflect about lessons learned in order to refine visualization design guidelines. And that comes back to the theoretical foundations part of that. And this is from a paper on the methodology of these design studies. So this is a project with two former postdocs, Michael Sedelmeier and Mariah Meyer. And we called it Reflections from the Trenches and from the Stacks because the trenches was that we'd actually ourselves done a lot of design studies between the three of us. We'd done more than 20 over about a decade, ranging back even before this term design study had been invented. Because that's a term I came up with a while back, around 2003 or 2004. And so one thing to notice when you look at these pictures, here is a bunch of different design studies. And if you just look at them at the pixel level, well, you see these are different screens, but we really do want to think about, what do they have in common? What do they not have in common? And that's where thinking about things in terms of abstractions and idioms is really helpful. And so in this paper, we provided some definitions. We had this idea that as we talked about, there's tasks, and sometimes these tasks are not very well understood. They're fuzzy. Sometimes they're quite crisp. And then there's also this idea from the data of, well, where is the information that you're dealing with? To what extent is it in people's heads, or has it actually been in some form made computationally available? Like, is it a thing we can compute on, or is it implicit, tacit knowledge in people's heads? And so, of course, if everything's in someone's head and there's nothing computable, well, we're not in a place where we could possibly do a design study. And if everything is well understood, if we're really clear on the task and everything is computable, maybe we don't even need visualization at all. Maybe we can do a completely automatic solution, whether it's writing a custom algorithm or using machine learning or something of that sort. But there's this big middle ground in between those where it's really a good match to have this idea of a design study where part of your goal, in fact, is to understand more about the task as you go through the process of designing at these different levels. And quite possibly you'll end up with more of the data in computable form by the end, but definitely you want to get progress on the task clarity axis. So in this paper, we proposed a 9-stage framework, starting with this idea of what I'll call a precondition phase where, first of all, you need to know about visualization. Interestingly, this idea of winnowing, of figuring out which collaborations are actually going to be effective and worthwhile, and how do you cast the people you're collaborating with into different roles, and be careful about whether you understand what role they might play in the project. And then this core stage where you're actually discovering what the abstractions are. So designing the idioms and then trying to implement that. And of course, actually deploying it, actually trying to get real world usage. And then finally near the end, where you want to reflect, what did I learn that anyone would care about who doesn't care about solving this very specific problem I solved? How can I reflect and find things that are more generalizable, more transferable? And of course, the process of writing itself, often in design studies, is a pretty substantial amount of time. These ideas out of social science of writing as research are very applicable here. A key thing, there's lots of arrows in this diagram. In general, any kind of these processes, they're always iterative. The nested model is also iterative, but I didn't actually include all the arrows in the picture, which sometimes led people to think that maybe it was just linear instead of iterative. So we have a lot of arrows in this diagram to really emphasize that you always end up going back. And a lot of what you learn at later stages, you can go back and iteratively refine something and then jump back forward to where you were after you understand the implications of that change. So typically these are highly, highly iterative approaches. The other thing we proposed in this paper was, and I think what a lot of people find the most useful in this is what to do wrong. A lot of my papers are, oof, I did this wrong, and maybe you could not do this wrong in the future, and you could learn from my mistakes, and maybe the mistakes of others as well. And so we identified a lot of pitfalls and gave advice on how to avoid them. I'm not going to walk through all of them in this talk, but we tied them to these different levels of the stages. So we had, again, almost 32 in total. So if you're curious, there's certainly a lot more in that paper. But what I wanted to do was just give you this way of thinking about them as a sort of framing for what I want to talk about, which is 3 particular design studies. So it's maybe interesting to note A lot of what I've talked about, well, it might sound a lot like user-centered design. And those of you with a human-computer interaction background might say, that's not a new idea. We've been doing user-centered design for decades in HCI. And so these ideas that we're doing a lot of iterative refinement, that you could deploy and actually see what happens with real-world usage, these are very well known in HCI. This idea that we could evaluate through deployment in the field and a sort of case study approach where you're looking at expert use. These are not new ideas. So what is new? What's specific to visualization? Well, the way I think about it, this is sort of where the nested model comes in, that it's really this process of discovering the task and the data abstractions is where we're really grappling with issues specific to Viz, and particularly with appropriate design of both the visual encoding and the interaction idioms. So it's these layers of the abstractions and the idioms is where we sort of customize the idea of user-centered design in a way that's really specific to visualization. So I'm going to talk through 3 case studies of problem-driven work. One's in e-commerce, one is in facilities management, and one's in biology. So let's start with the e-commerce one. So this was joint work with Kim Dexter-Romagino. It was actually presented at Euroviz a few years ago. And it's the Segmentifier system for interactive refinement of Clickstream data. So the idea is in e-commerce, there's a lot of creation of apps for large companies. And we were working with a collaboration partner, which was a middleware company that was exactly designed to help large companies create mobile applications. So we very much followed this idea of the design study methodology process, where we had a precondition phase that involved a lot of talking to employees of the company and trying to decide what might be a reasonable problem to attack. And once we'd really sorted that out and confirmed that it was a reasonable project to attack, then the core phase was almost a year, about 11 months, where there was a lot of iterative design and implementation, and then finally an analysis phase at the end with this reflection and writing. So let's talk about the abstractions. What are the task and data abstractions for analyzing clickstream data? Well, first, let's define it. What is clickstream data? So the idea is some users are, or in fact, a lot of users are trying to use some sort of a e-commerce website, so they take some actions. We can think of these, I'm going to use the word attributes. If we were thinking about tabular data, we can think about attributes as the columns, as opposed to the rows of the large table, which I'm going to call items. So we've got these different actions you can take, things like, okay, who is the client? What time was it done? What kinds of actions are there? And so as part of this abstraction, we found that, well, there was a lot of, sort of fundamentally different kinds of things they could do. They could add things to their cart. They could search on the site. They could actually buy stuff, often something that companies care a lot about. Various things about the functionality of the site. And then, of course, actually looking at a page view is a pretty central thing that people do on these websites. So there's actually a full hierarchy of actions in terms of page views. That's very much a rolled up, summarized thing. So there was some mid-level structure that we identified. So, there's different kinds of page views like, dealing with the cart, browsing, checking out, a lot of other things as well. And then we had a very detailed level. And a lot of the idea was to map any particular site, which might be large and complex, into this hierarchy of actions. And that was something that was sufficiently general that essentially all of the real-world data sets we looked at were able to fit fairly well into this generic, non-company specific hierarchy of actions. Okay, so what happens when people are looking at a website? Well, there's actually a sequence. They don't just do one thing, they do a sequence of page visits. So what we're going to call a client sequence is basically all the actions performed by a single user. And these are often lumped into sessions where basically as long as there wasn't a long timeout of say 30 minutes or more, then we think of this as a session. So we have user sessions, we have sequences of actions, and you can think of the sequences themselves as having attributes. Things like, well, when did it start? When did it end? How long was it? How many actions were there in that sequence? So I'm going to introduce this term called a segment, and all I mean by segment is just any set of sequences. So segments themselves also can have attributes, right? We can think about, well, how big are they? Both in sort of relative and absolute terms. And there's attributes like, again, you can inherit from all of the sessions within it, things like the start time and duration and how many things happened. And you can also think, once we've got these segments, about things like actions for a particular sequence, what happened before something, what happened after something. So it gets a bit more sophisticated than just single views. Now here's the thing. This might sound fairly straightforward, but in the real world, the issue is there are so many of these. The scale of this is huge, right? There might be millions of visitors every month. How do you actually make sense of analyzing a data set of this size? And moreover, it's not uniform. It's very highly variable. So you've got these huge and really noisy and highly variable data sets. So the problem is, although there's been a huge amount of work on trying to take, say, sequences and get structure out of them, it doesn't actually work on these really large data sets. So the real world data, we're completely unable to use a lot of these really interesting looking research papers. So we wanted to attack this problem of how do we segment, how do we chunk this sort of real world data into usable form? So the question is, well, what do people need to do when they're actually trying to analyze these click streams? What are the tasks? So we've talked about the data abstraction. Now let's talk about the task abstraction. So again, I'm going to introduce a word. I'm just going to say that behavior is any set of constraints of attribute constraints. So for example, you could think of behavior like, how many pages did you view? Did you buy something? When were you browsing? These are all things we can just sort of abstractly characterize as behavior. So one thing we can think about is, well, if your job is to actually analyze this clickstream data, what would you expect to happen? Like, surely before you buy something, you should add it to the cart. What might be more unexpected? Like, no purchases at all on a certain month if you'd actually had a history of buying things more regularly. There's things that the analysts know are good, like people actually bought stuff, favorable, and then unfavorable, bounced, is when you actually have people leaving the site before buying anything. That would certainly be considered unfavorable. So the idea is, what if you want to somehow take this huge, messy data set and find some segment that has interesting behavior, right? Well, that's a very general idea. What might that mean? So typically what you might do is you start with an entire, say, very large data set, and you want to refine down and get smaller and smaller segments until you get something that's both interesting and manageable. So you could distinguish more and more specific behaviors to partition the original segment down into something that is actually more tightly constrained. So you go from loose constraints to tighter constraints to see if you find something interesting. It might be interesting to see the frequency. How many sequences are there in that segment? So is it a large segment or a small one? Some things are interesting because of their order, right? It matters what order people do things in. So you might want to actually think about any sort of a ability to say something happened before something else. And so this idea of thinking, and this was refined quite a bit until we came up with this model, but after quite a lot of discussion and thought with these clickstream analysts, we came up with a model for what we thought of as a useful way to divide segments up. And so this high-level model is something that's not just sort of low-level abstractions of tasks and data, but a way to think more generally about this pretty uh, uh, general analysis pattern. And so the idea was, what if we want to take a really big, really noisy data set and refine it into segments that are small enough and clean enough that we could do something with them? Maybe we actually have something small enough that just using Segmentifier, we have some insider understanding. Or maybe we finally have gone from something big and noisy to something that is small enough that then we could feed it to the existing algorithms for doing things like pattern detection because we've tamed the noisy data set and gotten it into bite-sized pieces. So what we want to do is bridge the gap between these huge, messy real-world data sets and all of this existing work about doing pattern extraction from sequences. So this model starts out with the idea that there's viewing, because this is a visual data analysis model. So the idea is that there's always some person in the loop who's actually looking at a segment and trying to understand, what is happening with that. They're going to need to look at the segment. They're going to need to look at the sequence inside the segment and try to understand the actions in that. And what you're doing while viewing is you're trying to decide, okay, should I refine it further? Should I give up and abandon this segment as being uninteresting? Or have I declared victory and is it now time to export this segment? And so refining is where you say, well, let's take the segment and make a new one. Maybe we want to filter down. Maybe we want to chop it up into interesting pieces with partitioning. Maybe we need to do some other transformations. And one important thing about this system is this idea that we're actually automatically keeping a record of all of these decisions that the user makes so that they don't have to have any sort of mental overhead of keeping track of that. So what we want to do is automatically keep track of what kinds of questions they're asking, if they're doing any kind of hypothesis generation or hypothesis testing. And so we can actually allow you to then take one segment, try one hypothesis, then try another, try a third. And so it could be that the victory state is to export that for analysis with other specific algorithms, whether that's running clustering or pattern mining or something like that. You might conclude, you might say that in fact, even just viewing that segment has already shown you what you need to do. Or you might say, it's getting to the end of what I think I will learn from this segment. I can't see anything useful. I don't have ideas on how to refine it. I don't want to export it. So you abandon it and maybe move on to asking different analysis questions. So it's interesting to note, presumably a lot of you in the audience have already decided that visualization is useful, but what if you've got a skeptic that you have to convince, why are we bothering to do visual data analysis? Why don't we just have some completely automatic way of analyzing this data? It would be really nice if you could simply have an algorithm that handled data at this scale. But what we found is it was totally not realistic in this case. There were so many possible questions that an analyst could ask, and they really needed this data-driven interplay between finding the answers to a question, which often sparked new questions, and so on. So this sort of human-in-the-loop visual data analysis is really this idea of integrating computation and domain expert intuition. And of course, this is a very common use case in all kinds of visualization and visual analytics. So the solution that we proposed for this was this system called Segmentifier. And probably the easiest way to see what's going on with that is to watch a video. So let's actually roll that video.
One user session. Into the underlying data of the segment. The ranges section shows distributions of some of the major attributes. The actions section shows all information having to do with actions. For example, the analyst notices that only 41% of the sequences contain a page view. Marking this as odd, they go down to the sequence details view to take a look at the actual sequences. To help simplify them, they collapse all identical consecutive actions into one. They then notice that over 50% of the sequences contain only app-start actions, an action referring to the loading of a page, and conclude that there must be a tracking error. To filter out this noisy data, they select a sequence, which recreates the pattern in the Operation Builder. The Operation Builder view on the left is where analysts create operations to refine segments for each task. The analyst selects the Not option and clicks Apply to filter out the noisy data. The process is recorded in the Analysis Paths view. This is where the analyst keeps track of all operations and segments they create. Selecting a new segment causes the Segment Inspector view to update with the new underlying data. For example, now 99% of sequences contain a page view, which is closer to what is expected. The analyst uncollapses the sequences to get a more detailed view. They notice that over 50% of them contain only an app start and a page view action, represented by the L and V glyphs. In domain-specific language, This is referred to as a bounce. Wanting to further analyze this behavior, they select it, which recreates the pattern in the operation builder, and apply it to the segment. They select the resulting segment in order to investigate what types of pages people bounce from. To get further details on the type of pages viewed, they switch to the detailed level of the action hierarchy. This breaks up the page view action into the 17 page templates we derived. The contains chart allows them to immediately see the number of times each type of page was bounced from. In this case, they notice that the product description page makes up 71% of all bounced pages. Wanting to dive deeper to determine if a particular product page is causing issues, they download the segment to further analyze later. A benefit of the Segmentifier is that it allows analysts to go back and revisit segments to ask further questions. In this case, the analyst wants to further explore the previous segment. They can use the Action Transition Network to find out when app display errors occur. By selecting it, they can then use the adjacency view to determine which actions came before it. In this case, 36% of the time, it occurred after signing in. The analyst then decides they want to analyze the purchasing funnel. So they use the Actions operation builder to build a pattern with the 5 main actions required to purchase an item. They click Apply as Funnel, which applies the pattern to the segment step by step. The analyst can then select any of the resulting segments to investigate different steps of the funnel. In this case, however, they select the final segment to analyze sequences that have all 5 actions. The Operation Inspector shows the details of the operations applied to create the segment, so they are able to easily see the dropout at each level of the funnel. The analyst decides to further analyze purchasing behavior by creating a chart showing the distribution of the number of product pages visited.
I think this is a good place to end this video. Thanks. So that gives you some sense of Segmentifier in action and the kinds of analysis operations you can do with that. So the contributions of this project were that we really put a lot of effort into this abstractions for tasks in the data and really tried to characterize them both at the low level and with this higher level model of the analysis process. And so then we built a new interface for doing this process of refining data segments and viewing their characteristics in order to facilitate downstream fine-grained analysis. And we did do some validation in a sort of typical way with design studies of showing preliminary evidence of utility by actually getting some real-world Clickstream analysts from our collaboration company to try actually using this. And so we had an example of a multi-hour session where someone was using the Clickstream datasets from real-world data. We've anonymized those in the paper, but those are in fact from real clients of Mobify. So that was an e-commerce example. Now let's completely jump to a different domain and take a look at facilities management. So what can we learn from that? This is a paper with Michael Opperman, who just recently got his PhD last week and wrapped up and will be returning to Europe, to Vienna, in just a small number of days. So as part of his PhD, he worked on a project called Occupado, which was visualizing location-based counts over time across buildings. So with this project, and this was also presented at Euroviz, we have this idea of location-based counts. And so what do we mean by that? We mean, how do we actually see what's happening in a particular place where we're thinking about the counts of, who is actually in a building. And so it turns out to be pretty non-trivial to figure out what's happening in buildings. It's pretty expensive historically because people actually, would have to count the number of people in spaces or install specific hardware for that. And so any kind of visualization for building occupancy data was often quite limited to either a pretty small spatial location or very small time periods. So we wanted to deal with actually much larger data sets than people had looked at before. And so we did one of these problem-driven design studies to address this question. So there's this idea that we could actually use the number of mobile devices that are sensed by a Wi-Fi router as a way to have a proxy for actual human presence in buildings, because these days humans typically have multiple devices on them. And so we could actually account for how many devices are in a room at a particular time. And then a few minutes later, we could do that again. A few minutes later, we could do that again. And we can end up with a time series which shows how many devices are in some particular region of a building. Now, we could do this for many zones within buildings. Some of them smaller, some of them larger. And so we can end up with some idea of how many devices have been sensed over time in many, many different rooms and buildings. So we did this for actually campus level scale. So, relatively large spatial region with a bunch of buildings in it. And so we have this data abstraction where at regular intervals, say every 5 minutes, we're actually tracking a bunch of these location-based counts for how many devices are in rooms as a proxy for how many people might be in rooms. And so you can think of this either in, very small zones for individual routers or at the level of floors or buildings or multi-building campuses. And what's interesting about this approach is it's privacy preserving in that MAC addresses of individual devices are not being kept. They're actually not keeping device identifiers so that you cannot track individuals through trajectories. They're just tracking how many devices are in a room. So it has some advantages from the privacy point of view to have this approach. So this data had been used by our collaborators, a local startup in Vancouver called Sensible Building Solutions, Sensible Building Science, to actually control the air conditioning and heating systems in buildings to try to save energy. They actually came out of a sustainability group. And the interesting question was, could they take the same data that they were using to control building HVAC systems, and might there be people who want to use it for making decisions? So this decision-making approach was a very different use case than running HVAC systems. So we tried using these Wi-Fi connections, as I said, as a proxy for human use of buildings. And these are sort of, office or university kinds of buildings. So not just sort of single-family dwellings, but fairly busy buildings with a lot of people in and out. Now, this idea of Wi-Fi as a proxy for occupancy, the question was, well, who could actually use this to do something useful? And so we went and talked to many potential stakeholders who might be interested in understanding how, building resources are being used. And so we talked with the people that did space planning and, individual building managers, the people that ran the custodial services to clean up the buildings, people on university campuses trying to manage the use of classrooms, and also the startup itself wanted to understand, just how good was the data that they were getting out of their systems. So methodologically, we did this with a lot of semi-structured discussions and a lot of live demos in the spirit of iterative refinement, where we built a lot of tools as we went and then asked people questions about them. So some of the tasks were things like confirming assumptions or previous observations, right? Like for the facilities management people, are students actually in various rooms, say on evenings or weekends? For the janitors, would it be useful to go in and discover you had to clean up rooms if students were in them at unanticipated times? Sometimes it was monitoring utilization rates, like are rooms empty now? Are rooms busy? Are rooms that were planned to be busy actually being used? Communicating things to others and justifying decisions. For example, we sunk a bunch of money into renovating our building. Are the students actually using it more? Can we justify that? Validating the data, like quality control. For example, how small of a space could be captured. They already knew that things like single-person offices, it was not going to be reliable. But once you had larger rooms, they knew it would be, and they were interested in finding exactly what those boundaries were. So what was interesting about this from a data abstraction point of view is the granularity that was of interest. So in both space and in time. So we ended up building a number of visualization prototypes. We started out with what we'll call a sandbox, which was just, let's see what's happening at all. We got a static data export from the company early on, and using the spirit of data sketches of as quickly as possible seeing real data in a system, we did a lot of experiments to try to figure out, what techniques are effective, what is interesting in this data set. And we originally thought, well, we're talking to a lot of different stakeholders. We'll probably build one interface for each of them. But what we found was actually that didn't go as planned. The task and the data abstractions actually didn't break down according to stakeholder. We found that there was these interesting combinations of temporal and spatial granularity that multiple stakeholders cared about. And so when I say spatial granularities, I mean, for example, was it basically one room or a whole floor or a whole building? Those are the main regions that people were interested in. And in terms of time periods, right? Some people would be saying, well, I care about this space, every Monday from 9 a.m. to 10 a.m. That's when a particular class is. Or maybe the custodial people care about the last 12 hours. They want to know, was it heavily used recently? Maybe some people are looking at weekdays versus weekends, or summer term versus winter term, right? So there are all these different time slices that people might care about. So what we ended up doing is taking our initial sandbox for experiments, we ended up building 4 different prototypes. And there was a campus explorer where we actually were getting live data for an entire campus that was getting fed in, and it was useful for analyzing across multiple buildings. But then people often cared about things like, well, a single building but recent usage, or a single building but long-term usage, or just compare regions that could be anywhere across an entire campus at a pairwise level. And so what we ended up doing was not trying to reinvent the wheel for every one of these, but really thought about building reusable visualization components that would be useful across these multiple interfaces. And so in terms of the visual encoding design, one of the things we thought about was, when do we want to actually have these sort of very compact spark lines where we could juxtapose many of them side by side? That's good for things like patterns and trends and outliers. Things like box plot bars for repeating patterns. Confidence-based line charts where we were doing a lot of aggregation and showing min-max bands as we aggregated. Superimposed line charts. And these were all focused on temporal questions. And then there were also different spatial visualization components. It turns out people are interested very much in actually looking directly at floor plans and trying to understand different rooms usage, or looking at spatial heat maps. So we ended up building these different interfaces for Occupado. Here's examples of all 4 of those. And in this talk, I'm not going to go into great detail about any one of them. What I really wanted to emphasize was higher level, where the interesting part in this, I think, was abstracting data and tasks for looking at space utilization. So Occupado was actually not just a single interface, but a suite of tools for visual decision support. And I think the interesting part of that project was really the idea that we could have these very generalizable design choices that focused on a pretty interesting data set where we weren't looking at trajectories, which is often what people are doing with spatiotemporal data, but we were looking at this non-trajectory data that was really an interesting thing with much larger scale indoor environments than people had looked at before. Now, what's interesting about this methodologically is we did something actually a little bit different than that design study methodology I told you about earlier. So we ended up proposing a variation on this called Data First Design Studies, which we published at the Believe workshop, where we took that original DSM framework and we said, what if we change something and we say, before you decide who you're working with, you get a data set. Then, what kind of data is that? Are there quality challenges? What is so special about that kind of data? And so we said, who would benefit from looking at this kind of data? So to say that you actually, instead of first deciding on stakeholders and then figuring out what they need, we acquire data early and then do a lot of task elicitation with possible multiple stakeholders in order to figure out which of the data abstractions are actually applicable to which people and understand what their needs might be. Then you can go through and try to figure out if the stakeholders are a match for these particular kind of data. How frequently do they do these things? Are they actually important and central? Do enough people have to do it that it's of interest? And then it continued on with the previous design study methodology somewhat in a straightforward way. So we were really interested in what if you don't have stakeholders first, what if you have data first? That's why we call these data first design studies. So it's a bit of a different methodological framework, which might be interesting for other folks thinking along those lines. So now, and we've got a few minutes left, and I'm going to talk a bit about a biological case study. So in this one, this was joint work with Zipeng Liu, a PhD student who also just graduated last year, sorry, not last year, last week. Years and weeks, not the same. And also in collaboration with Shenghe Zhang, who was a PhD student in the biodiversity group. So with the Aggregated Dendrogram project, coming back to an old love of mine, which is phylogenetic trees, which are evolutionary relationships between organisms. And so as you might know, of course, all living things have genetic information, and biologists can reconstruct the phylogenetic tree of relationships between species directly from this genetic material. Now, the thing is, they don't just make one phylogenetic tree, they make lots of them. In fact, there's a lot of hypotheses about what phylogenetic trees might be possible given some sort of genetic base data. So biologists have to actually understand relationships between genes and many possible species trees. So there's trees of genes, there are trees of species, and they're trying to understand a lot of trees all at once. So you might have trees that were generated with different computational methods. You might be using different data sets to reconstruct these phylogenetic trees. So how could you have some sort of computational support for comparison of trees? Well, it's useful to think about previous systems in terms of how many trees they're comparing and how much you can see of each tree. And so there's been quite a bit of work on what if you really have a small number of trees and you want to look in detail, including some of my own previous work from decades ago, tree juxtaposer, where there's only a few trees and you want to see full detail. And there's also been a lot of work where you say, all right, I'm looking at, thousands of trees, and I really am only considering each tree as a point in high dimensional space. And those scale. But what if you actually need to see some kind of internals of these trees? What if there'd been some work about looking at dozens of trees at multiple scales, but there was really this gap where if you needed to see multiple scales and you had hundreds or even thousands of trees, what could you do? And so what we did in the Aggregated Dendrogram project was to really think hard at the idiom levels and at the algorithm level. So we came up with data and task abstractions for looking at these evolutionary trees. And we proposed a new visual encoding, and we called it this aggregated dendrogram. And we really wanted to have it be compact and focus on this intermediate level of structure with selected subtrees. And algorithmically, we wanted it to automatically adapt to how much screen real estate you give it. And so we also built a tool built around this idea of aggregated dendrograms as a visual encoding base. And so the ADView tool allowed multiple levels of tree comparison. So let's talk just a little bit about the data and the tasks. What are the characteristics of the tree data, and what are two of the most central tasks? So one important thing is that this is not just pairwise comparison. There is typically a reference tree that the biologists have, and then they've got a whole collection of other trees that they're comparing to this reference tree. And so that's one important aspect of it. And the tasks are, one is to understand the topology. What's the topological relationship between some subtree and leaf nodes? So for example, are they separated? Is one nested within the other? What's the topological edit distance between one leaf node and another leaf node found by traversing the tree? And the other task is about understanding the memberships of leaf nodes compared to the reference tree. So let's say you've got some subtree in the reference tree and you want to understand, is there an exact match in some other tree? Or is there only a partial match between where a subtree is in one of the reference trees compared to that new tree? So the idea with this aggregated dendrogram design, and I'll give you the intuition for that, is we wanted to basically compress a tree according to sections that the users explicitly said they cared about. So here on the right, we've got this glyph-like representation of tree structure, and let me just quickly walk you through that. So here we see that we've got, the user selected more blocks, and we're seeing a different glyph structure. So what is that glyph structure? Well, it's a focus plus context design where what we've got, and let me just sort of walk you through this piece by piece. We've got some trees that the user selects explicitly. Those are the focus nodes. And we're actually then hiding a huge amount of the internal structure of the tree and really just focused on the subtrees they've selected. We've got, if only some of the leaves match, then we have this bar that's only partially along this dotted line at the top. And anytime there's an exact match, we have these solid blocks. We explicitly show the number of leaf nodes because it turns out the biologists actually do need to know these numbers in addition to the topological structure. We show the proportion of trees that match the leaf set. And we show this simplified topological representation where in some cases we explicitly show that we are leaving out topological structure with this slash. And we show any sort of neighboring subtrees as context. Now we then show what the relationship between all these blocks is to some upstream root and try to show when there is additional context there as well. And if there's any missing leaf nodes, we actually have a little glyph for those on the bottom. Now what's interesting about this is we want to do this adaptively. So if there's enough space, we can show more, and if there's not very many pixels, we show less. So for example, here is the same set of selected nodes and trees that's optimized for 40 by 40 pixels or 80 by 80 pixels or 160 by 160 pixels. And notice how we show more structure when we have the pixel budget. So we built an interface that uses these aggregated dendrograms at its core. Again, I'm not going to go into great details about that in this talk. I wanted to give you a flavor for the kinds of things we were doing with turning data and task abstractions into visualization idioms. So at the high level, what we're doing is we have multi-level structure. So the reference tree is shown in full detail at the left. We've got a lot of histograms for showing information about different tree branches, which are also linked views that are selectable to this individual tree view. And that's where you can actually select these subtrees and blocks that you want to see on the right. So then in the main view, we have a lot of ways to look at various subsets of trees in the collection. And we cluster multiple aggregated dendrograms into these clusters of them, so we can see at an intermediate level of detail, and then finally in detail all of the trees in some collection. There's also things like information about individual trees, a high-dimensional representation of trees as points in a high-dimensional space, and then more ways to actually take a look at individual branches. Now, coming back to the idea of validation, we again took a case study approach with validating this, where throughout the design process, we worked very closely with the second author, who was a biology PhD student, using this kind of data for his analyses on a regular basis. And then we also went through and discussed with about 10 different biologists at different times to understand and verify, do we have the abstractions right? Are these kinds of tasks actually something that people were doing? And then in the end, instead of doing formative evaluation, we did summative evaluation, where we did do a user study with 5 different biologists, all using their own data sets with this tool. And they were able to see quite a lot of structure that was interesting and useful to them. Again, if you're interested in the details, I'll refer you to the paper. But in general, this confirmed that the task and data abstractions we'd proposed were actually valid and matched their intuitions, and that in order to do the tasks that they were doing, ADView actually helped them do that considerably faster. So I've taken you through a tour of problem-driven visualizations with design studies, and I focused quite a bit on the methods because methodology does matter. And I think it's useful to understand that identifying the abstractions, when you read the papers, they sound so clean and straightforward and easy. But typically, that was a very long process of iteration. Even after the tool is complete, it often takes a number of attempts to write about them in a way that helps people understand the generalizable principles that matter. And in these, there's often a selection of appropriate idioms. Sometimes you don't need to create new idioms and you use existing ones. Sometimes you really do need to design entirely new visual representations. And so I've walked us through 3 examples from different domains and different methods. So thanks very much for your attention for you this morning, for me this evening. There's more information about some of my own work if you're interested, and the book that was mentioned on visualization analysis and design. And we have a lot of papers and videos and software on both my research group site and my own personal site, and the talk slides are also up. And I would love to take a few questions.
Thank you very much, Tamara, for this great talk. Are there any questions from the audience? Otherwise, in the meantime, I have some questions. I assume that the engineering part in the core phase of the framework can be quite exhaustive. Do you have any recommendation on tool sets or tool chains or some directions the recent prototypes are going to be developed from a technical point of view?
We've used different tool chains in different contexts, and part of it is actually just, comfort and knowledge and preference of the first author. Certainly these days, many of our systems are in D3, and although some have been in R, are Shiny. So, depending on the context of use, for example, once we had to go with R because it was the only thing that they were allowed to use inside the CDC and actually install on their platforms. In other cases, D3 makes a lot of sense because it can just be browser deployed. One thing we've certainly found is a paper we're actually about to present in a few months at IEEE Viz on Viz snippets, also from Michael Opperman, has argued that it can be really useful to use a bunch of lightweight visual inspectors. And so the idea that instead of having one, that sometimes there's projects where instead of having one function, very high functional application, you might have a lot of little smaller ones. That was sort of what we alluded to in the Occupado project, and Michael took that even further with Viz snippets, which is looking at previews of visualization notebooks from things like Tableau and Observable. So one idea is, when do you have to go big monolithic, and when can you build lots of smaller little tools that might be really, really fast to build and deploy?
So this trend towards micro apps, so to say, high grade of modularity. And with respect to this, I asked myself, do you observe any connection between the fidelity of a prototype and the way the end user is going to accept it to be, I don't know, ease of use, for instance, and to be effective in use? Is there a connection between the fidelity in graphics quality or in speed and the success in actually using it in the deployment phase?
Yes and no. So, certainly at some point, speed does start to matter, and especially if you've got to do something that's scalable. But often, premature optimization is the root of many evils. And so typically what we usually do is we're usually much more interested in iterating on the design first, and then once we have a design we like, we worry about scalable algorithms. Because I don't want to spend, 6 months optimizing an algorithm only to discover, but wait, it's the wrong design. So often what we're doing is we are really focused on the rapid prototyping. And so Another thing we often do in terms of sometimes you can do rapid prototyping where you really don't want to get stuck into tiny little usability twiddles. So often in our work, we do a lot of what we're going to call chauffeured demos, where we are, say you're on a teleconference and you're sharing the screen, you have the user just tell you what they want to have happen, and the designer of the system is the one actually clicking on things with the mouse. So we're not worried about trying to train people, especially as the interface is iterating very quickly. So I think chauffeur demos is a way around low-level usability issues, because what we want to do is we want to find utility. We don't, if we've got utility, then we can get usability. But sometimes you can fine-tune usability, but you've completely missed the mark on utility. So I like these methods for quickly assessing utility before we worry about usability.
Okay, yeah, thank you.
Another Frage im Chat, oder? Im private chat?
There's a question in private chat. One moment.
I see it.
So Daniel Limberger asked, what is your recommendation to condense the great process you suggest in a 3 project to a smaller scale?
Well, one of those can be, decide where where is the key contribution. Most individual research papers don't have conclusions like at all levels of the nested model. It would be rare that you have something where you're doing a huge amount of work with data abstractions and designing a new visual encoding and having, new scalable algorithms to do that with. You typically pick only a subset. So I think trying to understand where is the low-hanging fruit of which piece of it do you really want to focus on? Is it more of the abstractions or more of the idiom design or more of the algorithm? So don't try to attack all of those at once. I would definitely try to scope them down in that way.
And thank you. And Helena Jambor asked, a lot of the project seems to have the luxury of being a long-term project, often in biomedicine. And she's involved in project only at the last minute. So I suggest, I think that does this have an impact on your process?
It does. I think depending on your goals, the question of, when do you have that luxury of time? I certainly have done some projects that have not been nearly as long duration. But often what I find is that to truly do a good design study, it usually does take a while. That typically, your first draft is just that, it's a draft. And then usually there does need to be a fair amount of iteration. I think that in general, if you know that there's not a huge amount of time, it can often be easier to make a technique-focused contribution rather than a problem-driven contribution. It's not trivial to do problem-driven work quickly. So, one of those things is, for example, sometimes it's a good match for a PhD student who can start a project and then be working on another project while, for example, waiting, after you iterate, then you usually need to deploy it for some number of months. That can be tricky for a master's student who wants to just finish up and get out. But a PhD student could start one project and then while that's being deployed, they could be starting something else. So the ability to interweave projects can sometimes get around some of these problems. But I think part of the design study methodology argument is if you don't find collaborators who do have the quality of time to engage with you for, maybe longer rather than shorter, maybe it's not the perfect collaboration. So sometimes you decide whether to work with people based on whether they have the quality of time to engage with you.
Yes, true. And I think for the last question, Chen He asked, regarding interaction design from the abstracted task, are there any principles to use besides the information seeking mantra? Broad question.
It is a broad question. I'm just trying to figure out how to answer that. I mean, the short answer is yes. I think there are some principles. So, this idea, sometimes overview first, zoom and filter details on demand. Sometimes that is exactly relevant, but there's times when it's not. I like, there was a project a few years back from Frank Van Ham, I believe was one of the co-authors, and this idea of you can't possibly show a global overview in certain situations. In their case, it was that you had enormous graphs and just showing all of them would be a hopeless hairball. And so they had this idea of, well, you start with some sort of query and then you expand on demand. So you have some starting point and then you expand outward. So you can't always go from the top down with overview and then details. Sometimes you start with the query and then move more broadly. I think some other sort of interesting interaction design ideas might be, how, I think I have to admit, I often start from the point of view that I think about visual encodings first. I think if I had more of an HCI background, I would often go deeper into the interaction design per se. But one of the things I argue in the book is that there's sort of 4 really large scale answers dealing with complexity. One is deriving new data. So this idea that you don't just take the data that you're given, but you transform it and then you visually encode the transformed data. Another approach really is entire families of interaction techniques where you interact a lot with a single view. But then there's a whole nother family of techniques that involve multiple linked views. And I think, how approaches for how to do linkage between multiple views, particularly with highlighting between them, is at the heart of a lot of the really interesting interaction questions. And then finally, using aggregation and filtering as ways of managing the complexity where you just cannot show every item in any of the views. And so that's sort of the 4 classes of techniques I think about where interaction is really just one of those.
All right. With respect to the time, thank you very much again, Tamara Munstner, for this presentation. And this closes the session. And we will have a short coffee break of 8 minutes. And then we start with session 4 on immersive analytics.
All right. Thank you very much for the invitation.
Thanks again.